Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum, dear students. Today we are going to learn about the consistency and Atterberg limits and the corresponding indices related with the Atterberg limits or consistency limits. So this is the lecture number 5. Course is Geotechnical Engineering 1. First we will start with the introduction of the soil consistency. Then we will touch a little bit about the history of the soil consistency. Then we will move towards the Atterberg or the consistency states: liquid, plastic, semi-solid and solid state. We will discuss then about the limits, which are liquid limit, plastic limit and shrinkage limit. Now in states, we divide the soil in those 4 states that if we are adding water content to the soil, how it's gonna behave, what would be the physical state of that particular soil. Now we will also discuss about the Atterberg limits determination procedures, methods, index properties which can be derived from those 3 limits. Plastic limit and shrinkage limit will give us the plasticity index, liquidity index, flow index, toughness index and the consistency index as well. We will also highlight the practical use or practical utility of those consistency limits and indices, civil engineering and in geotechnical engineering. We will solve problems and examples related to our today's topic. Now starting with the soil consistency. Soil consistency is the resistance to deformation or firmness, or in simple words we can say that if a soil is a very soft, firm, stiff, very stiff, hard. Later on we will talk about the qualitative and quantitative determination of what is very soft, what is very stiff or soft or firm and hard. We can qualitatively define these terms of the fine grained soils, which is the property of the soil consistency predominantly in the clay soils or in fine grained soils. Now this is the physical state of a fine grained soil at a particular water content. For example, if we are having a dry soil and we add 1% of water, if we are having dry soil and we add 10% of water, and if we are having a dry soil and we add 30% of water, and so on. Now the physical state of that particular fine grained soil will change, and that is known as consistency, and it will give plasticity to that soil, fine grained soil as well. Now depending upon the water content, a soil may appear in one of the 4 states: liquid state, plastic state, semi-solid state and solid state. Now if we draw the figure, on the x-axis we are having the water content, and on the y-axis we are having the volume. And if we are starting from the dry soil, initially if we are changing the water content, we will reach to a point that the soil will be saturated, and that limit will be known as the shrinkage limit, or SL. And this is the minimum water content at which the soil can be saturated, or the water content below which that any change in the water content won't cause any volumetric changes in the soil. Then if we increase the water content, we will reach to a point, this is the solid state, this will be the semi solid state. The soil will start to mold, and that is the start of the plastic state. This is the plastic limit. And then if you are increasing further water into the soil, it will behave as liquid, and this point will be known as the liquid limit. Now you can see here that from this point till this point, volumetric changes are occurring, and that is due to the change in the water content. So the water content is reduced from the liquid limit to the plastic limit, and the volumetric changes in that soil is occurring. Again, the volumetric changes are occurring here as well, and that is due to the change in water content from the plastic limit to the shrinkage limit. So basically we are having 4 consistency states. And 3 consistency limits. Same explanation is provided here. Solid, semi-solid, plastic and liquid states, and we are having shrinkage limit, plastic limit and liquid limit. Now in the plastic state, the soil can be molded without crumbling and rupturing, but if you are talking about the lower limit, at this particular water content, crumbling and rupturing will occur. In the middle there won't be any crumbling and rupturing of the soil. Here the soil will be kind of brittle. Here the soil will behave as plastically, and here the soil will be in the liquid form. We can relate that to the strength, compressibility and permeability characteristics as well, but that's been discussed in greater detail in coming slides. Now in 1911, a Swedish scientist Albert Atterberg proposed a series of tests to determine the 3 boundaries, limits between 4 consistency states, and the consistency states are liquid, plastic and semi-solid and solid, in which a soil may exist. Later in 1932, Casagrande presented the improved testing procedures which will be discussed in the liquid limit determination procedures in greater detail. Now, according to Atterberg, there are three consistency limits: liquid limit, plastic limit, and shrinkage limit. Pictures of Albert Atterberg and Arthur Casagrande are also shown in this particular slide. Now, starting with the four consistency states, we will start with the liquid state. Now, what are the properties of the liquid state? The soil will behave as a viscous liquid, and the soil will be having practically no resistance to flow, and the soil has virtually no shear strength. In the plastic state, the soil can be molded or worked into a new shape without crumbling and rupturing it. This is the stage when the soil changes from the possessing practically no strength, no shear strength, to having a limited shear strength. So the soil were having no shear strength. Now the soil water content has been reduced from the liquid state to the plastic state. Therefore, the soil is gaining some strength, and that will be in the plastic state. Now, what should be the property of the physical state? In the semi-solid state, the soil mass becomes brittle, and up to the semi-solid state, the reduction to the volume of the soil is very nearly equal to the volume of the water lost. Now, in this figure, we saw that the volumetric changes were occurring, but that change in volume and that change in volume from here till here was due to the water lost. Still, we can clearly see that the water content is present here, 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 and here. It will be 0% of water content. So from this figure we can see that the value of the shrinkage limit would be less than the plastic limit, and the value of the plastic limit would be less than the liquid limit, or we can say the water content liquid limit will be greater than the plastic limit. Plastic limit value would be greater than the shrinkage limit. Now, in the solid state, the sample begins to dry up at the surface, and the soil is no longer fully saturated. The loss of water is not accompanied by an equivalent reduction in the volume of the soil mass. Now, the loss of water is not accompanied, but till the semi-solid state, from the liquid till plastic and till semi-solid state, this state, the reduction in the volume was accompanied by the water lost from the soil mass. Let's take a sample and put it into the direct shear. Well, let's suppose first take a sample and second put it into the direct shear box. Now, direct shear box or direct shear test is performed to find out the shear strength of the soil, to find out the shear strength parameters, cohesion and friction angle, which will be discussed in Geotechnical Engineering 2 in greater detail. Now, if we put the sample from here, it will be having virtually no shear strength, when the soil won't provide any resistance. However, when we take a sample from here, now the water content has been reduced from the liquid limit till the plastic limit. You can clearly see that limited or some strength can be seen in that particular soil sample. If we take sample number, this is sample number 1, from here we will take sample number 2, and from here we will take the sample number 3, and now we can see that a greater strength can be obtained or greater stress will be required to strain this particular soil. If you want to make comparison with the strain level and the stress which the soil can take at that particular strain level, here 0 kilopascal is required to strain this particular sample number 1. Here, if you want to just give a number at 1% axial strain, how much stress we need to apply to strain this sample number 2 till 1%, approximately 10 kilopascal. But in this, at a shrinkage limit, or for the sample number 3 which has been taken at the shrinkage limit of that particular soil, in order to strain that soil sample till 1%, we need to apply approximately 30 kilopascal. Now from 0 to 10 kilopascal and from 10 to 30 kilopascal, so you can see. So now we can clearly see that by changing the water content, we can see different types of behavior from the soil. Now the moisture content at the point of transition from plastic to liquid state is the liquid limit, or we can also define that this is the transition from plastic to liquid state is the liquid limit, or the liquid limit is defined as the moisture content at which soil begins to behave as a liquid material or begins to flow. The minimum moisture content at which the soil can flow under a specified small disturbance force. No force or no stress is required to strain this specimen which is obtained from this soil, or we can say sample number 1. The moisture content at the point of transition from semi-solid to plastic state is the plastic limit. The moisture content at the point of transition from the semi-solid to plastic state is the plastic limit. Plastic limit can also be defined as the water content below which the soil can stop behaving like a plastic material. Now you can mold the specimen when you add water content into the soil, but there is a limit that the soil can be molded, and that limit is the water content below which the soil stops behaving like the plastic material, and the soil which allows it to be deformed without cracking or appreciable volumetric changes, that is known as the plastic material. The minimum moisture content at which the soil can be rolled into a thread approximately 3.2 mm in diameter without crumbling and rupture, and this will be explained in liquid limit determination, so plastic limit determination, when we are preparing a thread. When you see the cracks in your hands, in your fingers, these type of cracks building up, and the diameter of this thread is 3.2 millimeter. Now, moisture content or the water content reading at this particular point is known as the plastic limit. Now, what is shrinkage limit? The moisture content in percentage at which the transition from solid to semi-solid, solid to semi-solid state takes place is defined as the shrinkage limit. We can also define the shrinkage limit as the smallest water content at which the soil is saturated. It's the smallest water content at which the soil is saturated. It means that all the voids are filled with water. Also, it is the maximum water content below which the soil ceases to decrease in the volume on further drying. We explained in our figure here that it is the maximum water content that the volumetric changes won't occur. Here we are having water content. At this water content level also the volumetric changes won't occur, but this is not the highest water content. Here as well the water content readings are changing, but this is the highest water content that the soil volumetric changes won't occur. Maximum water content below which the soil ceases to decrease in volume on further drying. So this is the point. Maximum water content or the smallest water content at which the soil is saturated. Two methods are used around the world for liquid limit determination. First one is the Casagrande method. It's basically used predominantly in North America. There's a cone penetrometer method which is used in Europe and Asia. Now in Casagrande method, the moisture content in percentage is find out, but how we find out? We need to close a distance of approximately 13 millimeter, it's 12.7 millimeter along the bottom of the groove. After 25 blows is defined as the liquid limit, but it's difficult to obtain 25 blows in the first attempt. It's difficult. We need to perform few trials. So we first spray the soil sample with distilled water, then place soil paste in the brass cup. The groove is then cut at the center of the soil pad with the standard grooving tool. The cup is lifted and dropped from a height of 10 millimeter at 2 drops per second. Number of blows to close the groove of 12.7 millimeter are counted. So we need to record the number of blows, and we already know that it's difficult to adjust the moisture content to meet the required closure of the groove at 25 blows. So we need to perform few trials. At least 3 tests for the same soil are conducted at varying moisture contents, with the number of blows required to achieve closure varying between 15 till 35. blows. Now during the test we might face two conditions. One condition might be that if the number of blows are greater than 5, now we need to remix the entire soil, add distilled water to increase the moisture content so that number of drops required to meet the groove decreases. Now if number of blows are less than 15, then we need to add dry soil to it so that to decrease the water content, and standard reference is TMD 4318 for standard test methods for liquid limit can be used. Here are the accessories and the apparatus required: liquid limit device or Casa Grande apparatus, soil specimen, grooving tool, spatula, and moisture cans to find out the moisture content. So first you need to place the soil paste in the brass cup, then you make a groove in the mid, then you apply blows using this handle, and you will need to find out the closure here, and the closure should be approximately 13 millimeter or 12.7 millimeter. There are two types of grooving tools are used: Casa Grande grooving tools and alternative grooving tool. Here, this is the brass cup. The height of the soil paste should be 8 millimeter. At the top, the opening should be 11 millimeter. At the bottom, the groove opening should be 2 millimeter, and those dimensions are also given here and here using the Casa Grande grooving tool. You make a groove here, then you apply number of blows, 12.7 millimeter or approximately 13 millimeter, and you take soil sample in moisture can from here. After that, you go to your computer and you draw the number of blows on a logarithmic scale, moisture content in percentage on arithmetic scale. You plot these points in Excel and you draw that flow curve, and after that you will find out the corresponding water content for the 25 blows, and in this case it's 42%. That's how you will come up with a value of liquid limit equal to 42%. Now there is another method which is cone penetrometer method, fall cone method, and the British standard for that is also given. It's 1377. In the cone penetrometer test, a stainless steel cone 35 millimeter long with an apex angle of 30 degree and total mass of 80 grams, or we can say weight is equal to 0.78 Newton, is suspended above but just in contact with soil paste filled in the metal cup. Now the cone is permitted to fall freely for a period of 5 seconds. So you need to freely fall that for a period of 5 seconds. The penetration of the cone at varying moisture content is noted. Now the range is also given, which is 15 to 35 millimeter. Now the moisture content, this is important. The moisture content at 20 millimeter penetration is termed the cone penetration limit, which for practical purpose is the same as the liquid limit obtained by the Casagrande for n is equal to 25 blows. Okay, our number of blows is equal to 25, but in cone penetrometer or fall cone method it's 20 millimeter. Very important. Then you plot the penetration in millimeter and moisture content in percentage. For 20 millimeter penetration, you find out the moisture content required, and that is known as the liquid limit. So these are the data points, the number of trials which you made, and then you draw this line using Excel, the best fit line, and for 20 millimeter you find out the corresponding moisture content. Cone and the weight of the cone, the apex angle of the cone is 30 degree. Dimensions of the samples are also given. Now we find out the liquid limit. Now it's time to find out the plastic limit of the soil. Similarly, two methods are also used for plastic limit determination. One method is the ASTM D4318 method, which is glass plate method. The another method is the plastic limit determination using fall cone method. Now the procedure for the plastic limit test using the glass plate method is explained in greater detail in ASTM D4318, where you take a small quantity of soil, 15 to 20 grams is mixed with water. The soil paste is shaped into a ball, rolled into a thread on a glass plate with finger tips. Now the moisture of the threads is so adjusted that threads start just crumbling, cracking, rupturing at a particular diameter of 3.2 or approximately 3 millimeter. The moisture content of broken threads is determined and termed as the plastic limit. So you use your hand and finger. Now procedure is given in these figures as well, that you use certain accessories, glass plate, spatula, moisture cans, soil specimen, porcelain dish as well. You make an ellipsoidal soil mass and then you roll it using your fingers. And when they start crumbling at the diameter of 3.2 millimeter, that water content is known as the plastic limit of that soil. Like this is the minimum water content. Till that water content you can easily mold your specimen, and the soil can be molded at this particular water content. Now we can also find out the plastic limit using fall cone method, but you need to use a slightly heavier cone of 2.35 Newton. 3 to 4 tests are at varying moisture contents of the soil are conducted, and the corresponding cone penetrations or D in millimeters are determined. The moisture content corresponding to a cone penetration of D equals to 20 millimeter is the plastic limit. Now you perform 4 tests. For the liquid limit determination, and the weight of the cone was 0.78 Newton. Then you used a slightly heavier cone, which is 2.35 Newton, and you plotted the cone penetration in millimeters and moisture content in percentage, and then you find out the corresponding moisture content for both these cones. Now the moisture content for the lighter cone, which will be approximately 67% liquid limit in this case, and approximately here we will be having the plastic limit 55. I would call that as 55% is the plastic limit of this particular soil, or the Cambridge gold clay determined by the Falcon test. Now there is another limit, which is the shrinkage limit. Shrinkage limit test, we need to perform ASTM D4943 and is performed with a porcelain dish about 44 mm in diameter and about 12.7 mm height. The inside of the dish is coated with petroleum jelly and is then filled completely with wet soil. The excess soil standing above the edge of the dish is struck off with a straight edge. The mass of the wet soil inside the dish is recorded. The soil pad in the dish is then oven dried and the volume of the oven dried soil pad is determined. Using mercury, you place it in a porcelain dish where the mercury is there, and then you put that dry pad into it, and the displaced volume of the mercury will give us the volume of the dry soil pad. M1 mass of the soil in wet state and volume of the soil in wet condition, mass of the soil in dry state and volume of the soil in dry condition is noted down. Then you need to use this equation, which is the shrinkage limit SL. This is the shrinkage limit, equals to M1 minus M2 divided by M2 into 100 minus VI, and that VI is the initial volume of the wet soil, that is the inside volume of the dish. VF is the volume of the oven dried soil pad in cubic centimeter. What is rho W? Rho W is the density of water in gram per cubic centimeter, which is usually equal to 1. Now from these three Atterberg limits we can obtain the following index properties, such as plasticity index, liquidity index, flow index, toughness index, and the consistency index. Now the plasticity index is the difference between the liquid limit, this is the liquid limit, and PL is the plastic limit. So liquid limit is greater than the plastic limit, we will get a value, and if liquid limit is equal to the plastic limit, which means the PI is equal to 0, and if PI is 0, that soil is non-plastic. And if we are having greater PI, or the plasticity index is greater, it means that the soil will be having plasticity. Now plasticity index is important in classifying the fine grained soil as well, and the greater the PI, the greater the soil compressibility. So if we are having greater PI, plasticity index, greater that particular fine grained soil will be greater compressibility, will be having greater settlement. Now qualitative description would be something like this, that if you are having 0 PI, that would be non-plastic. If you are having 15 PI, then it will be medium plasticity, and if you are having PI value greater than 40, it will be having very high plasticity, and that particular fine grained soil will be having greater plasticity. Now there is another index property, and that is known as the liquidity index. The liquidity index can be find out using this equation, where W is the natural water content minus plastic limit divided by the plasticity index. We already know what is plasticity index. Plasticity index is liquid limit minus plastic limit, and W is the natural water content. Plastic limit we usually find out by making that 3.2 millimeter thread. So at plastic limit, liquidity index is equal to 0. At liquid limit, we are having liquidity index equal to 1, and if liquidity index is greater than 1, then this soil will be in the liquid state. We can also make a qualitative description here as well, that if liquidity index is less than 0, so we are having a semi-solid state. If we are having liquidity index in between 0 to 1, that would be we are having a plastic state. And this plastic state will be having intermediate strength, and the semi-solid state will be having high strength. The liquid state will be having low strength, and the soil deforms like a viscous fluid. Excuse me. Now the slope of the flow curve is called the flow index. If you remember, we performed 4 tests to find out the liquid limit, and then we plotted those 4 points and the best fit line. This is known as the flow curve. Now the slope of this flow curve is known as the flow index. For example, if we want to find out the slope of this flow curve, so this would be N1, N2, W1 and W2, and if you use this equation, you can easily find out the flow index. Similarly, there are other index properties as well, which you can relate it to the strength and compressibility characteristics of the soil. For example, the toughness index is the ratio of the plasticity index to the flow index, and the consistency index as well, where we are having the liquid limit minus the natural water content divided by the liquid limit minus plastic limit. So these are different indices which are useful for classification of the soils for engineering purposes, and these limits and indices are also related to the engineering properties of the soil, such as the strength and the compressibility and swelling and shrinkage potential. Now the qualitative determination for a very soft soil, this soil will be easily penetrated several centimeters by the fist. For a firm soil, it can be penetrated several centimeters by the thumb with moderate effort. Now for a harder soil, it can be indented with difficulty by the thumbnail. So that's the qualitative determination. Now let's have the quantitative determination. For example, for a very soft soil, the undrained shear strength of the soil, if you are finding from the unconfined compression test, it will be less than 12, and the standard penetration test value will be less than 2. We can also relate from the standard penetration test will give us this much of the less than 12 kilopascal of the undrained shear strength, and the consistency of this soil will be less than very soft. So we can comment on the strength of this particular soil when we know the consistency of the soil. For example, for the firm consistency soil, it will be having 25 to 50 kilopascal of the undrained shear strength, and the SPTN, or the standard penetration number, will be equal to in between 4 to 8. For a harder soil, it will be greater, the undrained shear strength will be greater than 200, and the standard penetration number would be greater than 30. Now cohesion is the attraction of one water molecule to another resulting from the hydrogen bonding, or we can call that as water to water bond. Adhesion, which is the plasticity addition, is similar to cohesion, except with adhesion involves the attraction of a water molecule to a non-water molecule or water to solid bond, which will give plasticity to the fine-grained soil. Now let's solve few problems, and very easy problems related to the shrinkage limit. For example, the volume, initial volume is given, final volume is given, and mass of the wet soil is given, mass of the dried soil is given. We need to find out the shrinkage limit. Now we already know the equation for the shrinkage limit. This is the m1, which is the wet mass, m2, which is the dried mass, divided by the dried mass into 100. Vi is the initial volume of the wet soil, final volume of the dried soil, mass of the dried soil raw of water, which is 1 gram per cubic centimeter, and into 100, and the given data is known. So if we just put those values in this equation, we will find out that the shrinkage limit is 17.2%. So it means that at 17.2% the soil is saturated, or the voids are filled with water at 17.28%. We can also say that at 17.2% is the maximum water content that won't cause any volumetric changes. Like the further drying, like if it's 5%, or if it's 10%, or if it's 17.2%, the volumetric changes won't occur in this particular soil. So this is the maximum water content in the soil, that if you are reducing it further moisture content, the volumetric changes for the 0 or 17.28% won't be different. Theoretically, test conducted on a soil sample gave the following results. Number of blows for 10, the water content is 60. For number of blows 19, the water content is 45.5, or for the water content of 39.8, the number of blows required to close that groove is 23. Again 27, 36.5, 40, and 25. So you can clearly see that the number of blows are increasing as the water content is decreasing. Then plastic limit values are given, 20.3% and 20.8%. We need to determine the liquid limit and plastic limit. We need to determine the plasticity index. We need to find out the liquidity index. At the water content 27.4%. We need to find out the void ratio at the liquid limit. We need to find out the void ratio at the GS, or the specific gravity, 2.7. If the soil were to be loaded to failure, would you expect a brittle failure? Now starting with the liquid limit, we can draw this data in Excel, in a graph paper. We can find out, if we draw this, if we plot these points in Excel, and we find out the corresponding water content for the 25 number of blows on a logarithmic scale and water content in percentage, you will find out that the liquid limit is equal to 38%. So plastic limit will be the average of the two values given in the problem statement. It's 20.6%. Plasticity index is equal to 17.4% and the liquidity index is 0.39. The natural water content is 27.4. Plastic limit is 20.6. Plasticity index is 17.4. And here we know that the phase relationship is there, and we need to find out the void ratio at the liquid limit. So at liquid limit, the as our soil is saturated, so we can take S equal to 1. So E would be at liquid limit, and the water content at liquid limit would be liquid limit into GS, and the liquid limit is 38. So we can use 38 into GS, and that is 2.7. So void ratio is 1.03. The answer to the if the soil were to be loaded to failure, would you expect a brittle failure, is no, because that if we are having liquidity index in between 0 and 1, we will be having a plastic state. So we won't be getting the brittle failure from this particular soil because the liquidity index is 0.39. Thank you very much, and I hope you are enjoying my videos. Please kindly like, share and subscribe to my YouTube channel. Assalamu alaikum and Allah Hafiz. Take care.